Thank you, Tim. Thanks to the department for hosting me and inviting me. Thanks to all of you for spending your Saturday mornings being here and listening in. I really appreciate it. And thanks to Michigan. I can't help but talk about Michigan before I go on. As Tim mentioned, I was an undergraduate here. And my first physics class was in this room. I used to sit up there. I have 3 sisters. One of us here who graduated from Michigan, a niece who just graduated 2 years ago. 2 of my senior staff scientists in my program, Dr. Chinese Forte, graduated with her PhD from Michigan a few years ago, and one of my other scientists, Silgi Park, was an undergraduate here in the geosciences before getting her PhD at Stanford. So I have Michigan in my roots, in my blood, and I continue to love this place, so I'm really happy to be back. Tim, today I'm going to talk about the future Oppenheimer feared, and not everybody, I'm sure, has seen the Oppenheimer film, but probably many of you have. So hands if you have. Okay, I do recommend it. It's a great movie, and you'll learn a lot. And I'm going to I'll go through some of the history, but sort of with a more physics bent, and talk about where we are today. So I'll skip ahead to today, what the world looks like having been shaped by nuclear weapons for all of these intervening decades, what the dangers and risks they pose today, and of course at the end I'd like to talk a bit about what we can all do about it. So briefly, because Tim mentioned, you might be unfamiliar with my organization. It's called the Union of Concerned Scientists. It was founded in 1969 by students and faculty from MIT. And at the time, they were seeing a lot of research funding going into weapons systems, and they wanted to see science used to solve society's problems instead. And more than 50 years later, we're an organization. It isn't a union, but it's an organization with around 250 staff. About a third of those are scientists and analysts. And we try to put rigorous science to work to build a healthier planet and a safer world. So we do technical analysis married with advocacy and communications and outreach to the public and to policymakers. If you're interested in this work, at the end I'll show you how to join us as a member. We have 500,000 members, and I can tell you more about those types of things, but it's a wonderful organization. Okay, so to orient us where we are today, who has nuclear weapons? At present, there are 9 countries in the world that have nuclear weapons, and it could have been a lot more. It's a wonderful success that there aren't hundreds. So while I'll tell you a lot of things about how the world is dangerous, I definitely want to say that we could be in a much worse place. That includes Russia, the United States, China, France, the United Kingdom, Pakistan, India, Israel, and North Korea. But it is important to note that the arsenals of Russia and the United States account for about 90% of these weapons. As for total numbers, according to the latest estimates, there are around 12,700 nuclear warheads in the world today, of which about 9,400 are in active military stockpiles. So given that a single nuclear weapon can destroy a major city and could kill millions of people, and dozens of such weapons could end a functioning society, it's important that we make sure we don't settle into complacency. So, how many of us here know what this is? Duck and cover. Yeah. So probably people who are older than me. I'm Gen X, so my sort of popular culture references are really centered around the nuclear threat. The films, the music, all of those things. But people who are a little older than me had duck and cover drills, civil defense in case of nuclear attack, and these kids were trying to protect themselves. It is sort of funny, but in a terrible way. So you had duck and cover drills, like the way in Michigan we have tornado drills today. This is what kids were supposed to do. So I am a little concerned that people who are in generations younger than me, while they, I think, have really keen sense of the dangers that climate change and its effects will have on our society and are really worried about it, I think because not growing up under the same type of experience as we had during the Cold War may not fully understand the implications of being handed this big, dangerous contraption of massive nuclear arsenals. So one of the things I really do try to speak to students and early career scientists and community groups about really where we are today to make sure that they understand this is as existential a threat as climate change is. I'm going to sort of return to the story where we're starting with the nuclear weapons story, and as in almost every topic of science, you could start sort of any place. It's a continuum, the accumulation of knowledge and intellectual effort. But I'm going to start with a story here because it's a great story, and this is a picture of Leo Szilard, who, as Tim mentioned, I had a lectureship for a year. I was meant to give these types of talks, sort of inspired by Leo Szilard, and he was a very interesting person. But where we are, so he's a little older in this picture than the story I'm going to tell. But so I'm going to start on a street corner on a rainy day in September 1933. So Leo Szilard was a Hungarian Jew who had fled first to Berlin and then to London. And he was furiously raising money to bring other scientists, refugee scientists, out of Nazi Germany because he saw what was going to happen. He literally got on the last train out from Berlin before they closed the borders. And that's going to be important later in the story because a lot of those refugee scientists were very important to the Manhattan Project. Another important thing about Szilard was that he was really good friends with Einstein during his days as a student in Berlin. In fact, they really liked each other. This will become important later in the story. And they even came up with a patent for a apparently ingenious but totally unusable kind of refrigerator. So they were good friends. Anyway, so back in London, Leo was walking and thinking, mostly about a comment that he had read in the newspapers from Lord Rutherford, the eminent English physicist, about the newly demonstrated technique of artificially inducing a transmutation of one element to another by bombarding it with a proton. And these reactions released a lot of energy, in perspective with an atom compared to the energy that the proton supplied. So it was sort of a source of energy. But Lord Rutherford stated that he thought that given the energy needed to create these reactions, that anyone who looked for a source of power in the transformation of atoms was talking moonshine. And Leo liked nothing more than finding a way to poke at people who made broad statements or who were in positions of authority. So he liked finding ways around things that were seemingly impossible. And in fact, later in his life, he treated his own bladder cancer with a radiation device he invented and cured himself. So that was the kind of guy. He was always thinking about ideas and implications. So between stepping off one corner of one side of the street and getting to the other side, Szilard had a brilliant idea, namely the chain reaction, the nuclear chain reaction. So the neutron had just been discovered by James Chadwick the year before, observed as a product of a nuclear reaction. So what if a nuclear reaction produced not just energy, but more neutrons than were used to generate that reaction? So maybe like one in and two out. It was conceivable. So if you needed one neutron incoming to produce energy, but the reaction released two, then those two atoms could generate energy and create reactions in the next two, and you tell two friends, and you tell two friends, and to continually input the energy of the first particle. So Szilard was the kind of person who ran his thought experiments to their final implications, and he was also keenly interested in politics, having really needed those skills in order to survive in what was to become Nazi Germany. So he thought one aspect of such a thing would be producing energy for positive human development and use. But the other implication was that a very fast and large sustained chain reaction would be an enormously powerful weapon. So he signed the patent. He was very into patents, and he was really good friends with Einstein, who was great at patents, so he picked up that skill. He assigned it to the British Admiralty because that was the only way he could think about keeping this idea secret. And he set about trying different types of materials to see if he could start a chain reaction. The nuclear science was very immature at that point, and people didn't know a ton about these things, and so he didn't have a lot of luck. And nuclear fission had not been observed or even really suspected at that time. So Szilard moved to New York, tried to cobble experiments together. He gave up believing there was a material that would actually be suitable. At the time, Enrico Fermi in Italy was exploring the materials and reactions that would be important, but no one was putting the whole picture together. That all changed in December 1938 when nuclear fission, the splitting of an atom into pieces, was observed experimentally by Otto Hahn and Fritz Strassmann, who turned to Lise Meitner and Otto Frisch to explain it theoretically. They predicted that the fission of the element uranium, the heaviest in the periodic table at that point, would produce additional neutrons. So Szilard, realizing his idea of nuclear, so in fact, he had just cabled, he was sick in the hospital with a fever, had just cabled the Admiralty, I give up, you can release this patent. The same day he got this news, and apparently, this is the story, got himself out of the hospital, went to the Western Union and telegraphed, forget I said that. Because he realized that his idea of a nuclear weapon powered by a fission chain reaction was a real possibility, and that any competent physicist, including the excellent German physicists he knew very well, would also realize the implications of nuclear fission. So he set to work getting the attention of the US government. So he went out to Long Island, where his friend Einstein had he was summering. Einstein had moved to the Institute for Advanced Study, and he convinced Einstein to write a letter to President Roosevelt, because he knew Einstein could speak to presidents. So he sort of invented this political strategy of getting your important, powerful friends to speak to the powers that be. And he wanted Einstein to persuade Roosevelt to start a research program that would look into these fissionable materials in nuclear fission. Einstein was a noted pacifist, and he has said that his only involvement in the Manhattan Project was as Szilard's mailbox, because he did this several more times as the years went on. So here's the physics. As most of you all know, eventually Szilard and Einstein and other scientists persuaded the Roosevelt government to start this top secret Manhattan Project beginning in 1941. And it was an enormous effort. It charged many of the best physicists and engineers in the country and assembled them to take this theoretical science and build it into a working weapon. So I think that the film Oppenheimer dramatizes this process really effectively. So scientists got to work and rapidly worked out the theory and performed the necessary experiments. In fact, so this book you can buy at many bookstores, and it's usually about $10. It's called the Los Alamos Primer. And the summer before the Manhattan Project, a bunch of these really smart physicists sat down and wrote everything they knew about the physics and how you might build an atomic bomb. And so they'd worked out most of it at the beginning. So a lot of the effort really was to find and refine the actual materials. But this is how it works. So for each fission, you get about 200 MeV, which is in the face of it, a small amount of energy. But for a normal chemical reaction where you're stripping off electrons or changing sort of the electron structure, usually those reactions are a few EV. So it's an enormous, orders of magnitude more per atom than normal chemical reactions. And that is really where the difference in nuclear weapons, the amount of power in a small amount of material. So the basic physics was worked out. Uranium is a very heavy element. It has 92 protons, which signifies its atomic number, and it has an atomic mass of 235, meaning it has 143 neutrons, so a lot of them. If uranium-235 is bombarded by a neutron of the right energy, it will more often than not break apart into two larger pieces, for example, the elements barium and krypton, and it will release, on average, a few more than 2 neutrons, sometimes less and sometimes more, but about 2 per reaction. And so you can calculate with sort of the normal density of uranium. It takes about 80 generations of fission to fission about a kilogram of material, and that'll take about a microsecond, which is a very fast reaction. Of course, the science was worked out. They needed to do a lot of experimentation to figure out the cross sections, the mean free paths, to work this out. But the basic physics had been worked out. So if you sort of calculate how much you need. So a critical mass means, so each of these reactions, if you have a nuclear fission and they release neutrons, you do need it to happen upon another uranium atom soon. You can't let it just stream out to the countryside. It needs to bump into the next uranium atom, before it leaves the surface. So you need enough material so it doesn't keep flying out. You need sort of a critical mass. And so using the measured cross sections and mean free paths, basically they were able to work it out to roughly, knowing that they would need about 52 kilograms of uranium. And plutonium was quickly realized, sort of a slightly heavier element, that was also going to be a great candidate for nuclear fission. And in fact, sort of a more effective material in that you didn't need quite as much. So you needed about 10 kilograms of plutonium. And there are ways to refine your design with neutron reflectors and shaping and doing different things to make that number smaller, which they worked out in intervening years. But so the reason I pick up this book is learning how to design the nuclear weapon wasn't the hard part. It was really being able to assemble the fissile materials, the uranium, enriched uranium, because only one isotope is really appropriate for this, and the plutonium, which doesn't occur naturally or barely ever. So it needs to be made in a nuclear reactor. So that turns out to be enormously lucky, because that is a technical bottleneck. That is one of the reasons there aren't hundreds of countries with nuclear weapons, because it's very hard to make and obtain these materials. So for example, the isotope of uranium you need for a nuclear weapon is uranium-235. And natural uranium that comes out of the ground in form of uranium ore is only 1/140th uranium-235, and the rest is uranium-238, which isn't useful. So you have to find a way to extract the good isotope from the isotope that basically reacts chemically, entirely identical chemically, and just barely heavier, barely lighter than the other isotopes. So there are lots of different ways that this industrial process to create this was enormous. In fact, figuring out how to enrich uranium and extract plutonium, they basically built something as big as the automobile industry at the time. That was the industrial effort needed to make these products. So in the Oppenheimer film, it really focuses on Los Alamos itself, but at the time, the real efforts were being made, for example, at Oak Ridge in Tennessee and in Hanford, Oak Ridge, Tennessee, where they're making the enriched uranium, and Hanford, Washington State, where they were making the plutonium. In fact, some people say that the people who lived there were some of the first victims of the nuclear age, because that was a very dirty process. Hanford, Washington is, I think, the largest Superfund site we have in the country today because of the work that was done there, and lives have been affected for decades because of this. So for your enriching uranium, there were a bunch of different engineering techniques designed to enrich and pull out those uraniums. They tried sort of ionizing and using an electrostatic force. Contemporary method is using gas centrifuges. So if you hear in the news talking about, does Iran have centrifuges? Where do they have them? What do they look like? The whole process there is to be able to enrich uranium to be able to be used in nuclear weapons. That's still a challenging engineering project. For plutonium, again, it doesn't occur naturally, so you have to make it in reactors. And that's a really slow process. You get about 8 kilograms per year from a small reactor. And then you have to extract the plutonium from the fuel rods. It's a dirty chemical process. So that is the key to keeping nuclear weapons not spreading, or we call them non-proliferation in our field, meaning they don't go to additional places that you don't mean them to go to. So they worked out the basic engineering, the basic concept of the nuclear weapon. So for the first nuclear weapon, Little Boy, which was the one used in Hiroshima, it used uranium-235, and it was basically a very, very simple design. In fact, to assemble the critical mass, so once you have a critical mass, you will have a nuclear explosion or supercritical mass. And so the design of it was really like a gun. There were rings made of uranium here, and an explosive, just a conventional type of explosive, sent a bolt to the middle, and when they assembled, that became a critical mass. In fact, the design was so simple, they didn't test it before using it. That type of design wouldn't work for plutonium because some physics reasons, they needed to assemble the critical mass faster. And so what they did instead was to have a not quite critical mass in a plutonium ball, and then to crush it symmetrically and make it denser from a symmetrical crush. And so a lot of the effort you may have seen in Oppenheimer, where they're blowing things up, they were trying to perfect the ability to, within a microsecond, have all of these conventional explosive aligned in sort of a soccer ball pattern around a metal to quickly crush it to a higher density and create a critical mass. They weren't entirely sure of that design, which is the reason that they tested it before in the Trinity test. So this is the gadget. They called it the gadget. This is the test that the bomb they used in the Trinity test. Scientists and engineers chose a site they described as suitably isolated, and they believed that the flat terrain out in the Tularosa Basin and the low winds would keep the fallout to a minimum. While they described it as isolated, there were about 500,000 people who lived within 150 miles of the Trinity site. Those people were not warned or told to evacuate, neither before or after the test. And those folks are absent from the Oppenheimer movie, so I do like to make sure they're part of the picture when we think about this. And this sort of negligence did become a regular feature of post-war nuclear test program, which included more than 200 above-ground nuclear explosions. Data collected by the National Cancer Institute showed that the fallout from those tests, the 200 above-ground nuclear tests that happened in the 50s and 60s, has led to tens to hundreds of thousands of excess cancers. Pretty much everybody who's alive after that has some residual material in their bodies from these tests. Some of these people have been able to get compensation from the government for this harm, although not the Trinity downwinders. But actually, right this moment in Congress is on the brink of instituting more compensation for these folks. So this is the Trinity. I'm just going to show a short video of the Trinity test. If you haven't seen
5, 4, 3, 2, 1.
In the dead silence of the morning, at 5:29:45 Mountain War time, the Jornada del Muerto was bathed in an intense flash of a light that man had only seen from the stars.
Would not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita, he should do his duty, and to impress him, takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.
So once they had confidence that this was a working weapon, this was near the end of World War II. Germany had surrendered. Hitler was no longer alive. But there was a decision to be made, and many of the scientists of the Manhattan Project at that time urged the government to, instead of using it against the Japanese, to instead do a demonstration. Leo Szilard is one of the ringleaders of that effort, to persuade to not use it as an instrument of war, and were unsuccessful. So in August 1945, a bomb was dropped on the city of Hiroshima, and then 3 days later on the city of Nagasaki. And tens of thousands of people immediately died. The estimates vary about the total number of people who perished or who were injured, but likely more than 200,000 people. And in the following weeks from radiation poisoning. Some of the scientists of the Manhattan Project thought, now people see what this can do. That's the end of war. Now we know. So the upside of this will mean we will have no appetite for ever using these again, and nobody will dare have any war in order to not risk this happening. In fact, and they thought, once we see this happening, we should put this technology under international control. But that isn't what happened. What Oppenheimer feared is what happened. So moving quickly beyond the fission weapon that we saw demonstrated in the video and the types that were used in Hiroshima and Nagasaki, there was a new type of weapon, the H-bomb, the thermonuclear weapon, the super. If you heard those words in the movie or if you've heard those words before, this is the modern type of nuclear weapon design, which essentially uses that fission bomb as a trigger for the larger bomb. So these rely on the fusion of light chemical elements, using the high pressure created by the fission bomb to create nuclear fusion and give enormously more yields, sort of many times larger. The first hydrogen bomb was 15 megatons, and the largest Soviet design was called Tsar Bomba. That was 100 megatons, compared to the Nagasaki and Hiroshima bombs, which were 20 and 15 kilotons. In fact, they looked like this. The tests were enormous. So those little dots around the perimeter of the circle, those are ships that were no one was on them, but they were instrumented to understand what happened in these tests. So the US had done its early tests in Nevada, but shifted its testing to the Pacific Islands, mostly the Marshall Islands. This was detonated over Bikini Atoll. So the Marshallese who lived there, that was their home. Many of them had to be evacuated, never able to return to their homes again. And during the Castle Bravo test, there was a Japanese fishing boat called the Lucky Dragon that was unlucky enough to be in the fallout area. And one of the fishermen died. The others had radiation poisoning. So these are enormously powerful. And so sometimes you don't completely understand what that actually means. So I have a little demonstration. I'm going to sort of show what I mean by bigger ones. So each of these fuse beads are, let's say we represent one of these as a sort of Hiroshima-sized nuclear weapon. So one of these little guys. So I'm going to take this jar of fuse beads and see how many. So today we have many nuclear weapons, and there are these thermonuclear ones, so much more powerful. What do you think the firepower is in the current arsenals of all the countries in the world that have the weapons, the 9 countries? You can shout out stop when you think when I got it. Anyone? Should I keep going? Each one of these is a Hiroshima bomb. And keep going? Stop? Keep. I need a new jar. I need 170,000. So at the peak of the numbers of nuclear weapons in the world, we'd need about 1 million. This is going to be about 170,000. Thank you to the team here, the physics demo team here at University of Michigan for organizing this for me. Yeah, this is a lot. Yeah. So that, when I was talking about the future Oppenheimer feared, he was worried about the super. He was worried about nuclear proliferation that other countries would want it. He was worried about what would happen if we didn't have nuclear weapons under international control, and that's where we are. So I promise it won't be we'll end on a not as bad a note as this, but it's pretty incredible once you see it. So to refine those designs and have different tailored effects, there were many nuclear explosions done, nuclear tests, most of them by the United States and the Soviet Union. You can see the dots represent, they're not to scale, but they are sizes of these explosions. I think, I've heard that Nevada is the most bombed place in the world, but most of the time, countries shifted these environmental burdens to places that were meant to be remote, but colonized people who were politically dispossessed and couldn't really argue about what was happening around them. For Kazakhstan, for example, in the Soviet Union, and the Marshall Islands for the United States. No countries are testing nuclear weapons today except for North Korea. There's been a moratorium. The United States stopped, I think, in 1992, and Russia at about the same time. India and Pakistan tested theirs in the late 90s. So that's a piece of good news, is that we're not doing this anymore. But again, to sort of orient you, the bomb yields are enormous. So the largest conventional weapons we have today are about 11 tons of TNT. The Hiroshima weapon was about 1,500 times larger. And again, our most powerful weapon ever detonated was 50 megatons. Super briefly, just what does a nuclear weapon do? So they're meant to be, now that we have them, militaries have plans for using them, and what are they meant to be used for? So the militarily useful attributes are the enormous blast pressure that they can destroy buildings and towns or deeply buried military targets. So there's a blast overpressure, and there's a wind that comes with that. So those are important for the military objectives, but they come naturally with other things that are really dangerous for people, including, especially if you're close by, nuclear radiation that will kill you immediately. Sometimes that will kill you in the next few weeks, even though you feel okay at first. Some of that, depending on how those bombs are detonated, sometimes they can suck up large amounts of soil and contaminate it and distribute it. So then you'll have local fallout or global fallout. So those have important widespread humanitarian effects that are not localized to their military use. So this is an example of a typical warhead that's in a US or Russian nuclear arsenal, about 455 kilotons. So most of the weapons are not these megaton weapons anymore. They're smaller than that. So if you orient yourself, you can see Manhattan sort of through the center of that, right where it's labeled New York, that's Manhattan. And so if this was sort of centered on there, actually, let's see, so the yellow circle you see is where the overpressure is about 5 pounds per square inch. So a normal unreinforced building would collapse people would be thrown, things would fall on them, and fires would start and become widespread. So because of the high temperatures of this thermal radiation, things like paper, trees, gas mains that are broken open, gas stations would catch fire. So there's a lot of fire effects. So enormous numbers if it's on a highly populated city, millions of people could die sort of right away. And the problem is you would also have a lot of injuries. And because the area of destruction is so large, it's right in the very places where the things you need to recover are located, like your hospitals, your power stations. All the emergency responders would be as damaged as everything else. So to recover, it would be extremely challenging. And of course, the transportation nodes. Again, so if, in the case of all-out massive war, where the kinds of war that the United States and the Soviet Union were sort of planning, not planning to do, but they had war plans, sort of assuming the 2012 arsenals, what would happen? In the United States, and it's such an attack, and these would normally not necessarily be on population centers, but targeted on industrial centers, which are often co-located with population centers, but not exclusively. Such an attack would immediately kill 60 million people and injure another 40 million. We certainly don't have enough hospital beds for the types of burn victims and radiations. They don't exist anywhere. And in Russia, such an attack would kill a larger percentage, because I believe their population is more concentrated in cities, which is an important effect. So you expect that many tens of millions more would die later from radiation poisoning and injuries. And lack of shelter, starvation, you'd stop all of your, our food shipping system is really dependent on, having just-in-time deliveries, petroleum reserves, all sorts of things. It can be very, very disruptive. And a longer-term issue, if the conditions happen to be right, where you catch a lot of fires, what can happen is that those fires can coalesce into what's called a firestorm. So not just normal fires, what happens is they coalesce into a big fire. So it's big enough that it starts to suck air in and swoosh up high enough that it can carry the soot from those fires up to the stratosphere, where they could potentially be long-lived because there are not that many processes that bring those out fast from the stratosphere. They don't rain out. And that can have climate change effects. So in the 80s, we talked about nuclear winter. If you were around during those years, that might be a familiar concept to you. Today, there's active research of colleagues who look at these models and do, how would it look today? Is this a possibility? And their research shows that even in a smaller nuclear exchange, for example, between India and Pakistan, may have the ability to create a firestorm if they're used on population centers that are heavily burnable. That would have implications for the rest of the world, and leaving potentially hundreds of millions or billions of people at risk of starvation because of the climate disruption. So it would be extremely catastrophic. I've already talked about this, the size of the arsenal, so I won't spend more time on that. But there was another innovation at the time that has important implications for us today. So in 1957, got to hear the launch of Sputnik. That was the only thing Sputnik really did, was beep. But enormous implications, because what launched Sputnik, so Sputnik itself wasn't such a revolution, didn't do much, but the rocket. So if you could build a rocket that could put something into space, which they did, this is a derivative of the same research program that the Soviets were using for an ICBM, Intercontinental Ballistic Missile. So if you have enough rocket power to launch a small thing into orbit, you have enough rocket power to deliver it around the other side of the world. So warfare previous to that had been really localized. You fly your plane to the place that you're going to do something. Your troops are forward-based. But this was now, the idea is you could mount an attack from across the world and not have any forward-based troops or anything. So obviously, clever scientists and engineers, thought that the marriage of the two technologies, putting a nuclear weapon on an ICBM, was the future. So that became enormously impactful because there was then a concern of sort of bolt out of the blue. And then the thing about these missiles is that they're big. They need to live somewhere. They usually will be put in, often in silos, where they're set with their nuclear weapon on them, reinforced, but they're pretty stationary, and so there's real concern that they would be vulnerable to an attack, especially when you have these powerful hydrogen bombs, which you don't need to target so precisely. But the technologies were developed, the ability to target using missiles. An enormous intellectual effort went into figuring out, gravity model to perfection, the ability to steer and compensate your rocket so that you could basically target from 10,000 kilometers away, target, this block or this part of this block on the other side of the world. So a lot of intellectual effort went into this. So eventually, as things happened, bureaucratic interests competed. The Navy wanted a nuclear mission. The Navy got submarines. The Air Force wanted a nuclear mission. The Air Force had the bombers and the ICBMs. But the implication of these types of really resting your nuclear weapons, your deterrence effect. So the idea eventually coalesced into, we can never defend, I hope I convinced you that you can't really defend yourself against a nuclear attack. They didn't know what to do with that information, but eventually coalesced on this, not even a strategy, but a fact of life that you're mutually vulnerable to each other. So what you're going to do is threaten ultimate destruction, and the threat of retaliation is enough to make sure you never initiate a nuclear war.
Mutually assured destruction was the expression, yeah.
Mutually assured destruction, yes, which was a fact rather than a strategy or an approach. It just was a fact. So that if you launch a nuclear war, your adversary will make sure that you are destroyed as well, and that was meant to deter anybody from starting one. But of course, there's all sorts of anxieties about, well, maybe I think I can catch your nuclear weapons before you launch them at me. I'm going to destroy them on the ground. So that's what led to some of these technologies. So there was a lot of anxiety about these missiles being put on the ground, and maybe my adversary can come and destroy them before I can use them back. And that would disrupt the mutually assured destruction. It would be like unilateral destruction, not mutual. So that drove a strategy to be able to launch these missiles at basically a moment's notice. Because a missile's traveling from the US to the Soviet Union or the other direction takes about 30 minutes. It goes up into space, basically where the lower satellites are living. It comes up and comes back down. It takes about a half an hour. So you have a half an hour between when you recognize that somebody's launched at you to decide, do I launch back? Do I move my missiles up and out of the way? So they created big systems in order to allow the detection of missiles coming at you and to allow a decision to use them right away. So they built these systems for speed. So big radars, space-based infrared satellites that could detect the launch of a missile, radars to see them coming, and a command and control system that was so responsive. It was really built for speed. So from the detection, from a Russian launch, so the infrared detection from a satellite recognizing there's a launch takes about a minute. Getting confirmation that that's what you see and typing it, no, it's not a short-range missile, no, it's not a space launch vehicle. I think I know what it is. I'm going to tell the military command. Then the president is notified and assembles his or her advisors and has to make a decision about what to do. The president gets debriefed, gets a list of options about what to do. The president decides to launch back or not. That's still only that president has only been deliberating for about 10 minutes. And if they go ahead and launch, and at about 21 minutes from the launch detection, the launch message for our response is received. The missiles are fired, and either the Russian bombs detonate or they never were coming in the first place. So that's a lot of time for such a consequential decision. I think we probably all agree that that is a system built for speed and not deliberation. Actual decision times could be shorter, and missiles can be launched from submarines, and so submarines are traveling the oceans, on constant patrol, and they could be significantly closer to their target. So that half an hour could be collapsed, in half for a submarine launch. So I'm going to take a minute to talk about some of the implications of that. So the good news is we all made it through the Cold War, but there are reasons. Sometimes we might not have. Given the way we set up these systems. This is an image of, I want to talk about this incident called the training tape incident. And this was in 1979. And sort of that day, the unthinkable happened. The computers at the North American Aerospace Defense Headquarters, NORAD, if you know that, it showed a large-scale Soviet missile attack underway. So just this thing, detecting the launches, seeing them coming, but lots of missiles. The launches came from Soviet silos and submarines off the West Coast, and they looked exactly like the kind of massive attack the United States dreaded. So the US nuclear bomber crews readied themselves to take off, and fighter interceptors took off. But when the communication with the US early warning stations, those radars didn't show anything coming. They didn't show any confirmation of what they were seeing on the screens. It was deemed a false alarm, and Pentagon officials were mystified. They didn't know why this happened. Later, investigators discovered that a technician was running a training tape on a computer that had a training exercise simulating a full-scale attack. Inexplicably, this showed on the regular NORAD screens. As far as a lot of the details are classified, but as far as we know, they weren't able to reproduce this error mode, weren't able to explain it, but it never happened again. So, crisis averted. No one lost any. No one launched anything. In 1983, there's a wonderful film called The Man Who Saved the World, and this is Colonel Stanislav Petrov. He was a Soviet officer who was on duty one day, and the Soviets had just created their own sort of early warning system, and he saw a similar thing on the screen, although it was just a couple of missiles coming, and he, by protocol, was supposed to notify his upper, his superiors, but he didn't think it looked like the kind of beginning of a nuclear war would look like. It seemed weird to him. So he held off a little bit and didn't report it up the chain. And eventually, they realized that the satellites mistook sunlight reflecting off the tops of clouds for missile launches. And the orbit used by the Soviet satellites was designed to minimize the chances of that, but the sort of the alignment of the autumn equinox, the satellites in the sun, and the US missile fields all sort of aligned in a way that this mistake could have been made. So of course, when you find the mistake, you fix that failure mode. But there have been dozens of close calls, and I'm sure plenty more that have not made it into the public domain. So we have been running risks. I guess is the main point here. So I'm going to skip history up until today to kind of orient you why I'm still so concerned, why it is not a cold, even though I'm using a lot of historical archival images, this is a today problem. This is not a Cold War, we're all finished with it. Of course, you can have escaped notice that in the Ukraine war, there's been increasing sort of saber rattling by Russian officials around using nuclear weapons in that conflict. There are more nuclear weapon states than there were. There are 9, so that makes for a more complex system than this sort of US-Soviet main dynamic. Again, as I mentioned, we still need to keep nuclear material out of the hands of people who might use it. There are new technologies such as cyber weapons, artificial intelligence, and anti-satellite weapons, all sorts of new things that start to intersect with these complicated systems of warning, command, and control for these systems that make predictability more challenging. And there is an incipient arms race that we're in. The US, Russia, and China are all investing in rebuilding and improving their nuclear arsenals. The US plans to spend $1 trillion to replace the bombers, the ICBMs, and the subs. Russia has recapitalized its own system, is building novel new weapon systems to get around US defenses. And China is also modernizing and expanding its nuclear weapons. And the US does not have good relationships with either Russia or China with which to diffuse these things. And the approach that we'd used before, arms control, which is how we went from having 1 million of those beads down to 170,000 of those beads, those treaties are starting to collapse. The United States has withdrawn from them. Russia is withdrawing from them. And the last nuclear treaty standing, the new START treaty, will expire in 2026, and Russia has already suspended its compliance with that treaty. So we are entering an era where we don't have the guardrails that we used to. It's much more complex, and there are a lot of nuclear threats that are in the air. But in the past, so that's the bad news. So I do want to say, how did we meet these challenges in the past? How did we deal with them? Because we did, in many ways. As I mentioned, arms control. The United States and Soviets got really good at negotiating with each other. This is a picture of a bilateral consultative commission, which is the group of technical people that meets in the New START treaty to talk about, I see you doing this, I want you to explain what you're doing, these are ways that not only do we constrain the numbers of nuclear weapons, because this treaty constrains the deployed nuclear weapons to around 1,550 for each of the two countries, but it allows a way to discuss nuclear risks with each other. And it did an amazing job. So if you look at this graph from the 50s to about today, these are the total number of nuclear warheads. So it isn't sized for capacity, it doesn't say how explosive they are, but this is pure numbers. And you can see we peaked at about 60,000, in the 80s, but we've really done a tremendous job at reducing those arsenals. We're down to about 10% of what that was. And so these treaties are really important. You can see as you do them, we're walking ourselves back from the brink. So those are really important techniques. I also wanted to point out that scientists, because we are here in a Science in the Morning talk, scientists have had a really unique role in this, not just the type of Szilard troublemaking, and he continued to work on these problems too, but they partnering with communities around their concerns. So on the left, that's Linus Pauling, who got a Nobel Peace Prize for his work organizing scientists to move nuclear tests, to advise for moving nuclear tests from being in the atmosphere to underground. In the 50s, some of you might have been around at that time. There was a big effort by communities to collect baby teeth in St. Louis to test them for strontium-90, evidence of fallout. So while these above-ground nuclear tests were happening, people didn't necessarily know that fallout was landing in their communities. So community groups collected teeth to get some data, and scientists jumped into this too, and Linus Pauling organized this, one of the people who organized this effort to provide the technical rationales for the partial test ban treaty, which moved nuclear tests underground. So tests underground continued, but there was, of course, an effort to stop nuclear testing at all, to stop this process of developing new and more refined, interesting designs to just stop nuclear tests. So on the right, this is Tom Cochrane, who was a physicist working for the National Resources Defense Council, and Evgeny Velikov, who was the chair of the Russian Academy of Sciences, and they wanted to convince their governments that it would be possible to verify a total ban on nuclear tests. So to support something called the Comprehensive Test Ban Treaty, which would stop nuclear weapons tests at all. And they got a bunch of seismologists and other types of scientists to carry equipment over, and the Soviets hosted like a demo experiment, sort of not a hackathon, but sort of like a hackathon, there to kind of show that this was a possible thing to do. And they both worked their own governments to lobby for signing on to a Comprehensive Test Ban Treaty, and were successful in getting that moving forward. And the public had a big role in this too, and I want to make sure that we acknowledge that. This is Coretta Scott King, who was really committed to nuclear abolition from her earliest days as an undergraduate. And she was very influential on her husband, Dr. Martin Luther King Jr., to include this as an important core piece of civil rights, believing that civil rights may not be important if we're not alive, and was very concerned about the amount of money that was being redirected into military spending when it could be better used for human development. So that was a core piece of that organizing in the 50s and 60s. This is June 1982, Central Park, New York. And Randall Forsberg famously galvanized a grassroots movement in the US called the Nuclear Freeze Movement, which was a simple call for a bilateral halt between the US and the Soviet Union on all nuclear weapons production. A million people showed up. There was a big concert, which sounded like I would have loved to go to that. Great people there, unusual, and was influential in putting public pressure on Ronald Reagan at the time. And then I'm going to shift to today. On the left, in the pink lay, that's my colleague, Lily Adams, who works as part of my team. And those are some of the Pacific Islanders who share this heritage, this legacy effect of the nuclear testing, and have been trying to get recognition and remediation and compensation for their harms. And on the right, this is the effort of other countries in the rest of the world, who are, most of them were not nuclear weapons countries who organized this, but to negotiate, to uplift the idea, the effects of the humanitarian effects of nuclear weapons, to make sure people understood that research was being done to better understand it, and that those implications were impactful in policy making. So over an effort of a number of years, they got political support, organized treaty negotiations in the United Nations system to negotiate a treaty called the Treaty on TPNW, Treaty on the Prohibition of Nuclear Weapons, which prohibits the production, use, testing, hosting of nuclear weapons. And it went into force and ratified, and the team behind it won the Nobel Peace Prize for their efforts. And catching up with you today, as it turns out, even though most people aren't always thinking about nuclear weapons, when asked, on average, people in the United States, nuclear weapons are not popular across the aisle. This is not a Democrat-Republican thing. This is a widely held sentiment in the American people that no countries should be allowed to have nuclear weapons. It's really interesting results and something that indicates some ways to make progress. And so I think I wanted to land back on, this is a picture of Szilard and Einstein. I just wanted to point to some of these interesting techniques that they've tried and sort of invented different ways to get at this problem, writing petitions, asking your famous friends to help, organizing scientists. Wherever you are, whatever your particular place in society is, there's a role for you, a thing for you to do. So I'd like to challenge you to think about what, even in a small part of your day, you might have to offer here. And I'm going to land on, this, which is a picture I took last fall. This is in Hiroshima. These are students, and this is the Children's Memorial at Hiroshima. And they have a real community education effort to make sure that the victims of the nuclear bombings were not forgotten, and that we encourage people to commit to peace. So they came to pay their respects at the Children's Memorial. They had songs and poems that they prepared, and were really just wonderful and hopeful. So I'm going to leave it on this, and I'd be happy to talk to you about ideas for solutions or to take questions on the technology or the history, and thanks again for coming.
Thank you so much, Laura, for that assessment and telling us where we are, where we could go. We'll have the question and answer. We're getting that set up. We'll have microphones here in the room. If you'd like to ask a question, they're in both aisles. And we've gotten a few online, so we'll start in just a moment.
Hi.
Okay, let's start here.
I have two questions. I don't know which should go first. One is, since we're not next to banning all nuclear power, as you were pointing out, U.S. and Russia are both in a new process of updating, upgrading their stockpiles and their silos. Can the fuel that's in the old ones be reused in the new ones, or do we have to keep refining more uranium? My other question is, where you almost got, is there any way to circle back to the idea of international control?
Thank you. Those are both great questions. So, in fact, the first question, which I'll rephrase for people, we are redoing our nuclear in the United States and lots of other countries. We are refurbishing, modernizing existing nuclear weapons. The question was, can we use the old nuclear materials, or do we have to produce new nuclear materials? So that's an active research question, actually. One of my colleagues in my program is doing a big technical report on it, looking at what's called plutonium pit production. So plutonium is a new material. It hasn't even been around for 100 years, so you don't know everything about it. But we think it is, from we have big labs, scientific labs in the United States that study questions like this. So there's active research trying to understand the material properties of plutonium and how it ages. So it's an active scientific question that a number of bodies have weighed in on and have assessed that they probably last in excess of 100 years, 120 years. But we're looking carefully at what they're saying and into the details. But we have plenty of plutonium. So that's not necessary, especially since we've reduced so much. The problem is more, what do you do with all of the stuff that you've made? So there are different ways into different techniques that you can do to make those not usable by somebody who might happen upon them. And then the second question was, are we close to international control? I don't think we are.
Close.
Is there a path? Is there a path? So, the way nuclear weapons used now are so firmly lodged in each country's individual security. I would like to see. I absolutely think it's essential that our future goes there, and getting from here to there is really challenging. So, and we do need a strong United Nations, which isn't particularly strong right now. We do need people working hard on treaties. So I think we're eventually, when we get to low numbers, that's where we have to be. But so we're trying to methodically look at different paths there, but it's tricky. Yeah.
You actually have several questions online, so I wanted to insert one now.
Okay.
Which is to talk about, well, the question was specifically about the Star Wars program and the feasibility of it, but maybe you could just talk more generally about
Missile defense.
countermeasures, missile defense, yeah.
So there's a program in the 80s that President Ronald Reagan initiated. So he was as horrified as I hope you were today by our vulnerability to nuclear weapons, and thought that was an untenable way to live your life under such threat, which I agree, and did not like that the only way we're trying to be safe is by threatening destruction of somebody else, that didn't seem like a great strategy. So he thought, United States has enormous technical and economic resources. We must be able to escape this vulnerability, and we must be able to stop those missiles before they come. And so initiated a project called Strategic Defense Initiative, but people nicknamed it Star Wars pretty quickly because of the impracticality of this question, because it turns out it's extremely hard. And they had sort of invented all sorts of technologies, or they had aspired to technologies that were not either impractical or not going to work at all, to try to escape this vulnerability. But it was impactful politically because it was something that sort of disrupted this agreement between mutual assured destruction. And so, in fact, it played a spoiler role when Gorbachev and Reagan met, and they had almost agreed to abolish nuclear weapons. And but it was sort of contingent on the United States giving up this approach to SDI. That I think this is how this. I'm not a historian, so there's details I might not have quite right. And we didn't want to, and so we've quickly abandoned that approach. I'm not sure their advisors would have loved that they agreed to get rid of nuclear weapons, but they were open to the idea. So then those plans came back to the ground and tried to have, sort of smaller, different approaches to try to knock down these missiles as they're coming towards you. And then we still have programs today that are meant to try to destroy nuclear. So nuclear weapons are in like a reentry vehicle packaged in a big hard casing as they fly through space as a way to destroy those as they're coming. But really, it's only, it's even challenging to do against a state like North Korea that has very few resources. It's just a very hard problem. So it's never should really be considered as a way to escape this essential vulnerability.
Thanks.
So we often talk about the civilization ending risk by the nuclear bomb. Mm-hmm. And people believe that human beings can be terminated because of the nuclear bomb. But I also have thought that it will be really the hatred and then cruelty of human beings to kill each other, indeed, which will eventually lead to destroy the human being. So the nuclear bomb could be one of the tools, but it wouldn't really matter which would be the definite tool. If there's a huge party of people who's willing to kill each other, they will try to kill other people by all means. So I was trying to ask, in this regard, in your opinion, can we be still confident enough to say the nuclear bomb is the strongest and greatest weapon at all times on Earth? 80 years ago, in 1985 and 45, it was obviously no doubt that nuclear weapon was absolutely the strongest weapon on Earth. And I also believe that way whole time. But going through the COVID, my thoughts shifted a little bit. And, I'm really curious that, human beings have not been able to come up with any better or stronger technology compared to nuclear yet. Because I was also thinking about if that you showed the map when the nuclear bomb was detonated, and then I also imagined what if the COVID was detonated that way? It's gonna kill people in a couple of days, and so is the nuclear still be the only matter that we have to discuss as a special issue, or is it really can we just talk? Nuclear, in my opinion, nuclear may not be the only matter that we have to discuss about this, the well-being of the human being. We also need to talk about all the technologies that can be potentially put human beings in danger. And then most of all, I think it's important to tell people, instead of intimidating people by talking about the impact of the nuclear bomb, I think it's more important to tell people, let's not hate each other, and then we need to get harmonized, and then don't get to the point that we want to kill each other. I think I thought that part might be more important compared to talking about the impact of the nuclear bomb, I thought. So that was long, but that was my question actually. Do you still believe that nuclear weapon is the strongest thing after all?
Thank you. Actually, you're not going to get an argument from me about what you said. I think there's no way I don't think we ever get to the end where we need to be with just a technological fix. right? You do have to find a way to exist better with each other and not and minimize the reasons countries go to war and have a more global sense of security rather than national security. I think that's definitely got to be part of the solution. And I've certainly been to these, had talks and experiences where I think what I'm doing is not nearly as important as artists and humanitarians who are working on those very things you said, trying to make sure that we lessen our impulses to destroy each other. So the reason, though, that I think that I spend my career on doing this is that nuclear weapons are just an order scale just so much bigger and more and worse. You can, yes, for example, a hammer can be a tool and it can kill somebody, but you have to do, but a gun is designed to kill and kill quickly. So there's an order of magnitude difference between nuclear weapons and regular weapons. You don't have to send hundreds of airplanes. In one bomb, you can destroy a city. So your worst impulses are married with something that has immediate, irreversible, destructive intent, which is really, I think, why I work at that nexus. There are lots of threats, I think, that we need to be paying attention to, and there are probably weapons. I don't know enough about how to assess the way people talk about generalized AI, whether that truly has the types of threats that people ascribe to them. But the worst weapon I know about is nuclear weapons, and we know they exist, and we know what they do. So, but thanks for those comments. I take them to heart.
Let me inject a technical question, or maybe two. One of them is the mushroom cloud. Whether that was actually anticipated, do you know, before the Trinity test?
That's a good question. I don't know if they've done those calculations. That's not something that I know. And just to catch, a mushroom cloud is really the iconic thing that when you see it, that's what you think a nuclear weapon is about. And I almost never use that image because it really privileges the people who are doing the bombing and not the people who are on the other side of it. So I try not to use that image a lot, but what happens is it's a huge amount of hot material goes up, and as it cools, it down. And I think that is married with this idea of fallout, and I think maybe that's what your question was. Were they really prepared for the extent of the fallout that would have come from Trinity? I don't know how well they were prepared for that. I think they waited on the weather to try to, increase success. I think they did make allowances to try to make sure that if their intuition about what would happen was correct, that there was that it wouldn't harm that many people. But I don't know what they knew about it.
They did detonate bombs over Japan at tens of thousands of feet, and the Trinity test was at a few hundred feet.
Yeah.
So there was some calculations
That's
that
right.
must have been done in terms of the effectiveness based on that.
I have two questions. One is, it seems that we've gone along a long time with mutual destruction being able to prevent war. But third parties who might not have much interest in it other than destroying the rest of the world, what are those threats right now? And the other is, how close are we to using fusion to generate power, electrical power? That's the climate change issue, I know.
Yeah. Okay, so there's a lot of questions there. So wait, the first one was
Third parties.
but there's one before that. No.
No, that was the first one. That I feel that third parties are more likely to cause
Yeah. Okay. So what are we doing
massive
about?
destruction of the earth.
Okay. No, but in fact, there's something I didn't want to let slide because you said because a lot of people will ascribe the relative lack of conventional conflict to mutual assured destruction, and I don't want to be so quick to give it all the credit or much of the credit. I think the jury is out on that. It's a matter of a lot of debate. Because we also had better economic and cultural integration of countries. We were sick of war. and really wanted to build international systems of cooperation. So I think we have to allow that those also had a lot to do with not having war during the mutual assured destruction. Okay, so third parties. So like way back at the beginning of the talk, I hope the point I was trying to take away is the bottleneck here is getting your hands on fissile materials. So a third party is very unlikely to be able to successfully build, a really well-working cascade of centrifuges unless it has the support, economic and logistical support. That's a pretty sophisticated organization. So not a sort of run everyday one, or the ability to create plutonium in a reactor and extract it. But so the real thing you got to do is get all of those under lock and key as much as possible. So after the Soviet Union collapsed, the U.S. had a huge effort to go to Soviet Russia and make sure all those Soviet scientists were gainfully employed, that we all had a shared idea of what keeping things under lock and key were. And in the Obama administration, there was a big effort also to really go out into the world and identify where are these materials, where do they need to be, can we pull them under better security, and to try to really get a handle on that. Because once you have your hands on that, I mean, it's a very hard problem. It's a much easier problem if you can make sure nobody gets those materials. And so that's where the effort really goes. I don't have any inside assessment about where we are on that, but I think we're doing pretty well. Yeah.
Thank you.
Thanks.
That actually specifically addressed another of the online questions.
Okay,
good. A state sponsor would be required for a terrorist to acquire a bomb or build.
More or less, yeah, depending.
Some kind of, yeah.
Yeah. Where are we? Here?
Hi.
Hi.
The Union of Concerned Scientists, I've always thought, has been primarily known for its contributions to making people aware of the risks of nuclear destruction. I think that a lot could be done by starting to elevate making people aware of the possibilities of improving life on Earth. I think UCA could do a lot of that. I think in the current political competition, some people could be talking about how much Russia and China would be better off if they were trying to make the world a better place for everyone, including themselves, rather than trying to expand their control over a small area. And admitting that the U.S. does a lot of bad things, but that if we started working more together, we could do a lot of things. I've always struggled with how do you actually think about putting some sort of international control over nuclear power without having those people then controlling everybody. But I think that you could work on that. You could start by modeling how to wipe out an aggressor with a small amount of nuclears without causing the storm clouds, perhaps. But anyway, if you have any thoughts on that or could start implementing it, I'd appreciate it.
Okay, thank you for the suggestion. We always try to be solutions-oriented. I skipped that slide here, but I have a number of things we're trying to do to address this particular problem rather than like transforming society at large, although we do have efforts, especially to work with other scientists, like-minded scientists, to have those similar things happen elsewhere, right? Not just a U.S. problem, but point taken, thank you. Yeah.
I did want to mention that the movie A Compassionate Spy does give a very different view of the release of the atomic information to the Soviet Union, and a different view of a lot of the different issues. I thought Oppenheimer, the movie, biased things a lot toward kind of saying that it was kind of natural that the U.S. had to go the way it did, and that gives a very different view. So I encourage you. I think it was Netflix or one of the other ones that still has it. Yeah.
So A Compassionate Spy is a film about one of the young scientists, was a very young scientist who, during his, he took a trip home for his birthday. He walked into a Soviet consulate and offered to explain what the U.S. was doing in the hopes that we would have a shared sense of responsibility for the technology, and the U.S. wouldn't use it to be hegemonic, I think, essentially. So it was a good movie. I appreciated it, too. Thanks. Yeah.
Chuck?
Yeah, as bad as nuclear technology has been, or it could be, we have another technology now that was recently accidentally or naturally demonstrated in 2019 with COVID, the possibility of biological warfare. And I think it might be able to be better controlled, but if we're not doing it now, not controlling it now, it's gonna get worse.
Yeah. We tolerate a lot.
Question from online. Is a false alarm, you told us two incidents.
Yes.
Is a false alarm more likely to start a nuclear war than aggression?
Well, so, I don't have a quantitative way to assess risk like that. So I wouldn't assign numbers to that, but I certainly think countries, the people in charge of such things are acutely aware of most of what I've shown you today, that they would be enormously destructive, and the consequences of intentionally starting a war. But I do think that mistakes, miscalculations, misinterpretations, and false alarms. It doesn't even necessarily need to be a false alarm. It might be not understanding the signals that your adversary is trying to send you. They might be trying to send you a back off signal, and you read their signal as we're about to attack you, so you should attack us. So there's lots of room for those types of mistakes in a system that you've primed for rapid decision making. That's really the piece that concerns me the most, is the requirement that you make decisions often, or not the requirement, but it's set up for you to do so. So I am very concerned about mistakes, miscalculations, and false alarms.
I kind of have two questions, I guess. I know we're low on time, so maybe you can take your pick. But one of them was just, I was curious to hear more about, like, I know that one of the goals is reducing the number of nuclear weapons, and I was wondering what happens to those that we've already built, if you could maybe talk about that more in detail. And then I was also wondering a little bit about, in terms of modern applications, I remember hearing on the news stuff about, like, Russia considering using, like, tactical nukes in Ukraine and, like, smaller weapons that aren't necessarily as massively destructive, and, like, you know, so far that's kind of taboo, but, like, is that a possible future that we would have to worry about?
Sorry, the first question again?
Yeah, what happens to the nukes?
Yeah, okay.
Yeah.
So we know how to disassemble them because we have disassembled thousands. So, you can take apart the missiles and whatnot. And the pits, the piece that's really the thing that you're worried about, the fissile materials. In the United States, I believe the disposition of those are all done at a plant in Texas called Pantex. But I'm not an expert in how the storage and the ultimate way you dispose of them in a way that can't be retrieved later. I think that's an active technology question. And then you asked about Russian tactical nuclear weapons. And so I'm going to show you what tactical nuclear weapons aren't one of these. Tactical nuclear weapons are like, 10 of these, right? So that's how you should think about them. They're not tiny little weapons that do a little bit of a thing. They're almost always more powerful than the Hiroshima and Nagasaki weapons. So it's a real concern because there is some suggestion that Russia might be thinking, or somebody might think that by using a smaller nuclear weapon, they can say, we are ready to escalate this to a general nuclear war that you don't want, so we want you to back off. And that would be a signal. And this is what I'm talking about, misinterpretation. Is that signal interpreted correctly? I think nobody knows what happens on the other side of any kind of nuclear use. And the risks of things getting out of control, I think, are way too high to contemplate being cavalier about using them in some way to spur some other kind of reaction by your adversary or to warn them off. And they're not generally sort of battlefield useful. It's not the way you destroy a bunch of tanks. It's not it's not a useful weapon for those types of situations anyway. They're really a political weapon.
Yeah. Thanks.
I think to be quantitative, a conventional bomb that can destroy a building or tanks is maybe at most 10 tons. And these weapons, or even tactical weapons, are 10 kilotons, 1,000 times more, is that right?
More than that.
More than that.
Yeah.
A lot of buildings. Question here?
Okay. So you've said that the fissile material, luckily, is hard to come by, and so terrorist organizations would not be able to easily get their hands on this. But earlier in your talk, you talked about uranium-235 versus 238, and that, sorry, I'm sorry, the 235 is the one that we use for making this, but the 238, most of it is what uranium is easily found in that form. What is the likelihood of that ever being able to be used and therefore being so much more available in a quantity? And I'm sorry if that's an easy physics question, but I have no idea why 235 versus 238 is the preferred one for nuclear weapons versus totally useless, thankfully.
Yeah.
So
no, thank you. That's a great
basically
question.
my question.
So your question is, well, I explained, hopefully, but this went by really fast, that uranium-235 is the right isotope for these reactions, and uranium-238 is not, which is great because there is a lot of uranium-238 around the world, and if people were dropping rocks on other rocks, we would probably have nuclear, if they were critical in these huge tons, we would have nuclear explosions all the time. So it doesn't work. The physics doesn't work. And the work that it takes to get the 235, when you hear the word enriched uranium, low enriched uranium, high enriched uranium, that's the percentage of the isotope uranium-235 compared to 238. And so that's an intensive, as I said, either mechanical process or chemical process or some way to concentrate that, and that's a hard problem. So we're not going to, the physics won't work that you can use uranium-238 for a bomb, but varying levels of enrichment for the material, you can do different bomb designs. It doesn't have to be the best bomb in the world, but you really do need to, a minimum effort is not enough to get the material into something you'd use for a bomb. It really is a technical bottleneck that is, I don't envision a way really around it. Yeah.
Well, with that, thanks so much for coming back to Ann Arbor, for bringing your expertise.